Hello, my name is Amanda, and welcome to the Math and Physics Resource Center online at Saginaw Valley State University. Today we're going to be looking at the Calculus 1, Math 161 topic of Riemann sums. Riemann sums give an estimate to integrals whether you know the function or not. They give a different estimate based on what endpoint you choose to look at it from. You can look at it either through the left endpoint, the right endpoint, or through the middle point. Doing this will create an estimate based on how many sections you want to divide the area under the curve into. So the Riemann sum can only be found for a defined interval, and you need to know how accurate you want it to be. So based on your n value is how many sections you're dividing it into. So in this case scenario, we're going to be dividing the section from 0 to 5 of this function here that we don't know. And we're going to be estimating the integral value from 0 to 5. So we're finding the area under the curve from 0 to 5. And dividing it into 5 sections. So that means the difference, the dx, the difference between each section, so the thickness of each section, because we're just making a bunch of rectangles that we're going to take the area of in order to estimate the whole area under the curve. So our difference is going to be that total length of the entire section, which is going to be from 0 to 5, so the whole length of the sections. It's going to be 5 minus 0. Our b minus a, if you will, our start point and our end point, and it's going to be dividing by the amount of sections. So 5 minus 0 divided by 5, it's going to give us 1. So our dx is going to be 1. So now when we're looking at left Riemann sum specifically, we're going to be taking it from the left endpoints. So that means we're going to be looking at the left endpoints from 0 to 5 dividing into 5 sections. So that means we're going to look at the left endpoint at the endpoint at 0, this endpoint at 1, 2, 3, 4, and that's it, because we will not be doing the 5 because it's the left endpoints. Let's write the summation logically of what endpoints we're going to be taking. So dx, the difference between the thickness of each section, is going to be the same for each section. So we can do 1 times, and then we're going to find the height of each section. So from 0 to 4, we're going to have f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. So that's following that setup summation that we have. So now we're going to look at the endpoint at 0, the left endpoint, because we're following from the left. So 0 to 1. So we just draw across. So we find the endpoint on the left of the section, and we just draw it across. That's going to be the height of the entire section. So now we're going to look at the left endpoint at 1. So that's at 0, so there's really nothing there. And then at 2. Then at 3. And at 4. So this is our area. So now our estimate is only going to include the area that we have drawn here, which gives a pretty accurate estimate, but it's obviously going to be an underestimate because of all this space that's not being included. Since we're taking it from the left, we're going to start at the 4, and then we're going to stop here. The reason why we don't take the value of the 5 is because it's already accounted for in the section because we took it from the left endpoint. So the function of f of 0, that's going to be at 1. At f of 1, that's 0. Plus f of 2 is going to be at 1. So what we're doing here is we're taking the area of each of these rectangles because we're multiplying height, which is this value, times thickness, which is 1. We just divided it out in a way that's going to, because the thickness is the same for all of them. And it's going to be plus 1. It's going to be 4. And then the one at 4 is going to be 9. So if we add that all up, we're going to have 15 times 1, which is just going to be 15. So the estimate of the area under the curve from 0 to 5 using the left endpoints of each of the sections is going to be about 15. So now let's move on to find the right Riemann sum of the same function. So we're going to be doing the same process, but instead of taking the endpoints from the left, we're going to be taking them from the right to create our rectangles, to create our sections. So the thickness is going to be the exact same as the previous because it's still 5 long and dividing it into 5 sections. So, but this time we're going to be taking the f of x values, the function values from 1 to 5 because we're corresponding to the right endpoints of each section. So we're going to have 1 times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. So now let's draw our rectangles on the graph. So from 0 to 1, we're going to take the endpoint starting at 1, so that's around 0. We're going to start taking the endpoint at the right at 2. We're going to take the endpoint in at 3. We're going to take the endpoint at 4. And now we're going to take it at 5. So now the area that is drawn is the area that we're going to be accounting for to get our estimate. Now, unlike the left's Riemann sum, where it looks like it's an underestimate, this one is obviously an overestimate, so we're going to be accounting for more. So our value is going to be higher than the actual value. So now we're going to evaluate. So at f of 1, it's at 0. At f of 2, it's at 1. At f of 3, it's at 4. At f of 4, it's at 9. And at f of 5, it's at 16. And this adds up to be 30. So the right Riemann sum estimate is going to be 30, which is probably going to be, which is higher, which is an overestimate. We're going to be looking at the midpoint Riemann sum. So instead of looking at the left and right endpoints, we're going to be looking at the center and the center points and creating our sections from there. First thing we're going to do is we're going to create the summation. So the summation is going to go from 0.5, so right here, and it's going to go all the way to 4.5, because again, you're taking that value of the function from the midpoint of the section, and we're separating it into 5 sections. So that means we're going to multiply by the thickness, which will be the same for each section, which will still be 1, because the distance of each box is still going to take up 1. So it's going to be 1, and that's going to be times the function at 0.5, well, the value of the function at 0.5, the value of the function when it is at 1.5, the value of the function when it is at 2.5, plus the value of the function when it is at 3.5, and plus the value of the function when it's at 4.5. So let's show what that looks like on the graph. So we're going to take it from the center point of that section. So from 0 to 1 section, we're going to take it from the center point, and it's going to be super short right there. From 1 to 2, again, it's going to be super short again. It's kind of hard to tell. From 2 to 3, it's going to be right about there. From 3 to 4, the midpoint's going to be right around there. From 4 to 5, the midpoint's going to be right about there. So now that we have it all drawn, you're going to notice that unlike the left endpoint that primarily went underestimating, and the right endpoint primarily overestimated, this one under and overestimates. That's why of the 3 Riemann sum methods, the midpoint is the most accurate. So now let's sum it up and get an estimate. So from 0 to 1, that midpoint at 0.5, that's going to be roughly, we'll say 0.5 in value. And I'll say the same between 1 and 2. From 2 to 3, the midpoint is roughly at 2. From 3 to 4, the midpoint's at about 6. And from 4 to 5, that midpoint is at about 12. So we're going to add that up. If you add that up, you get 21. So that means we're estimating the integral using midpoint sum to be 21, which makes sense that it is in between our previous two estimates for left and right. So now let's check the accuracy. Shown from finding each Riemann sum, they're all giving varying estimates, while the actual value of the integral of this function from 0 to 5 is 21.6 repeating. As shown from our values found, the left is an underestimate, the right is an overestimate, and the middle is the closest. But it's still not 100% accurate. But this shows how Riemann sum can give you somewhat of accurate answers when you don't know the function. And the accuracy will increase based on the number of number of sections, because obviously if you had more sections, it's going to get tighter to the curve. So then all the area that's accounted for, there will be less empty area. While in our previous examples, there's a lot of extra space accounted for, or a lot of unaccounted for extra space. While the middle has a balance of both, it has a little extra and a little less, the more sections you have will definitely increase the accuracy. This is the basics of Riemann sum when working with smaller n intervals. Usually if you do use a higher number of n's, you're going to use a computer program because doing it by hand would be very challenging and very time consuming. Thank you for watching, and thank you for visiting the Math and Physics Resource Center for SVSU Online.